All right, everybody. So we spent the last few lessons going over the different aspects of line of best fit, how to be able to use that line of best fit to predict something. Um, Today we are going to be looking at how reliable that line is. And so what we have done before is we found a correlation coefficient and we were able to test if that correlation is significant or not. And so now we are going to be doing we a sort of similar thing for the line of best fit. But there is no hypothesis testing involved in this method. And so these are the three definitions that we are going to go through. Uh, and so these are basically measures uh, of how much of the deviation can be explained by the independent variable versus it being something else. And I'll explain this a bit more later. So first off is the definitions of these words. Um, so initially, explained deviation is essentially the deviation that is explained, the deviation of the dependent variable that is explained by the independent variable. So how much of the changes of the dependent variable depends on the independent variable? Um, an example of this that we talked about before is age and blood pressure, right? Uh, and so the question is, so the explained deviation is basically telling us, okay, uh, how much of the change in blood pressure is actually explained by age? And so the next part, the unexplained deviation, is the opposite of that. It is the deviation of the dependent variable that is not able to be explained by the independent variable. So this is the deviation that might come from other factors, such as maybe in the case of age and blood pressure, maybe it's the diet, maybe it's other medical conditions, maybe it's just how early you woke up that day. These are things that are affecting blood pressure that is not the independent variable we identified, which is age. Um, the total deviation is just simply the combined sum of the explained deviation and the unexplained deviation. So essentially just all the differences combined. And all these have different formulas that we can use to calculate it. Starting from the explained deviation, uh, the explained deviation is the sum of each individual dependent value subtracted from the mean of the y values squared. So what this looks like is the sum of yi minus the mean of y squared. And so this is what this looks like. And again, I'll show you an example in a second. For now, I want you to just be able to write this equation down. The unexplained deviation, oh sorry, this is y hat y. The unexplained deviation is the difference between the individual y's and the mean. So this is what I had previously. The sum of yi minus y hat I squared. The total deviation, you can calculate it in two ways. if you already know the explained deviation and unexplained deviation, you can simply just add them. So this is explained deviation. Oh, sorry about that. Deviation. Let me just use the text format actually. So this could just be the explained deviation plus the unexplained deviation. This is one way you can calculate it, assuming that you already know the above deviations. If you do not know those, however, you can calculate it by each individual y values subtracted by the mean of y squared. All right, so before we move on, let me just show you what this looks like in an actual numerical scenarios, because right now that's a lot of words and a lot of formulas. So let me switch over to this. Okay. Just have this. Okay, so you can still see the formula on the side there. I'll move it over a little bit. Okay. And so right now we have age and blood pressure. This will just be our standard example. I'm gonna be uploading this sheet onto Google Classroom so you can look at it and play around with it as you see fit. So the things I need, just to recall, the y hat, and I'll put this up here, y hat represents the predicted value. Y hat represents the predicted value. Y bar, anything with a bar on top, we have already discussed, means the average, right? And so that's the first thing we need to do. So age will be my independent variable, and blood pressure will be my dependent variable. So that's my x and my y. And so first, let's find the average of my y's. And I'm going to put that up here. I'm going to highlight this in blue. This is equals the average of my y's, BB. So my average blood pressure that I have is 151.2. This is my y bar. Next, I need to find all of my y hats, my predicted value. Now, what I could do is use the slope and y-intercept. So slope of an intercept, BBAA. And I have this, right? If you don't understand what I just did there, you might need to go back and review what we did for line of best fit, because that is essentially what I just did there. And I can use this to predict each of the values given the x, right? So when the age is 16, it would be 16 multiplied by 1.71 plus 80.3. And that would be by predicted y values. And let me just use this as this column, predicted y value. And I can do that. If I put an equal sign here, this will give me 107.66. The other way I can do it is to use the forecast method. So equals forecast. I want my x value here, and then my data, y, x. And that would give me a close enough answer. There's, again, you can see that there's some rounding things going on, but overall, it's close enough. So I'm just going to go ahead and autofill that. If it did not show the autofill, you can click this blue square, drag it down, and all of that will be in here. I'm going to quickly reduce the number of decimal points. 2 is plenty. And I'm going to erase this. Okay. All right. So far, that should be things that we have already done. Um, so let me just explain these really quickly. So at the age of 16, when I measured a real life person, I got a blood pressure of 109. Um, Based on my line, my prediction would have been that this person has a blood pressure of 107.5. So my prediction was a little off, right? I was off in my prediction by about 2. Um, for the age of 25, the actual blood pressure ended up being 122. Uh, and my prediction was 122.89, which is really good. That's a really good prediction. Um, let's look at some of these other ones. 39, I was off by about 3. The 45-year-old, I was off by a lot. I was off by almost 25 points there. Um, Same with the person with the age of 49. I was off by another 30-ish. 64, I was pretty close. 70, I was really close. 29, I was close. 57, I was close. 22, I was close. So I was close for most of these data points, right? And so now let's find my explained variation, explained, unexplained, and I will do total later. Okay. And so my explained deviation is I need to subtract each of my predicted values from the mean. So I need to do, for the first one, I need to do 107.54 minus 151.2, right? Remember that this up here is my mean. And I could just do that for each of them. I could do an equal sign and keep doing that for all of them. So 122.89 equals 122.89 minus 151.2, and just do that. Alternatively, the easier way would be to do equals. I want to do this minus 151.2. And that way I can just drag this down and it would automatically do all of it for me. You can also change this to a cell. So C1, yes, C1, which is this cell up here. Now, the thing is, I don't want this number to change, right? I don't want this to be moving up, down, left, right. So I will have to put dollar signs there so that when I drag down, it won't change. So that's one way you can do it. The final part here, I need to square each of these values. So what I could do is in each of these, I'm just going to go ahead and square them. Square each of these values. And then I'm going to add them up, right? So sum of the above. Again, I'm going to reduce the decimal places a little bit. Right. Let me move this over a little bit so that you only need to see the formula. For unexplained deviation, it will be each of the actual y values minus the y hat. So equals each of the actual y values, so the data that is given, minus my predicted values. And again, I can autofill that. This last one, I need this to be, I also need to square these, right? So I need to square these. Square all of these, and I need to add these all up. Again, gonna lower the decimal points. Okay. And that's pretty much all I need to do here. Since I have the explained, since I have the explained deviation and the unexplained deviation, the total deviation is just these two added together. So my total deviation is about 10,900. Pretty much 9,000 is explainable by the by age. So 9,000 of the 10,900 of the deviations is explainable by age, and another 2000 is explainable by other values. For example, the other 2000 that is unexplained might be able to be explained by diet, by what time you woke up, by do you do sports, and all these other factors. Um, I hope that makes sense so far. If not, you can come to the Google Classroom and I can explain more there. Um, for the total deviation, just to show you how to do it, if I just asked you for the total deviation, then that means you don't have to go through these process, right? So the total deviation, let me bring this back, is each of the actual y values subtracted from the mean of y squared. So equals each of the actual y values minus the mean squared. Again, I don't want the mean to be changing, so I'm going to keep that as always C1. Alternatively, you can just do 151.2. That's also fine. I'm going to drag that down. And that gives me, if I just sum up, let me erase this. If I just sum up all of these, oh, sorry. Sum up all of these, I should get pretty much the same number, right? 10,900. So both methods work. It just depends on what you want to find. If I tell you to only find the unexplained deviation, then this column is all you need to do. If I ask you to find the explained deviation, this column is all you need to do. If I ask you to find all three, you don't need to do the total column. You can just do explained, unexplained, and then add up to get the total, right? So you don't need to do all three for most of the scenarios, but you should be able to know how to do them. Okay. So moving on, there are two more things that we need to go over. And let me switch back to my slide here. Slides. Okay. So we are now going to be talking about the coefficient of determination, which is just a long way of saying, of asking what percentage of the line of best fit is reliable. The coefficient of determination is, by definition, the ratio of the explained deviation to the total variation. That is the official definition. In other words, it's just the explained deviation all over the total deviation. This one up here over this one down here. There is another way to calculate this, and a much easier way to calculate it is that this is actually the same as r squared. So just as a reminder, r is our correlation coefficient, right? We all should know how to do that on Google Sheets by now. It's equals correl. All we really need to do is square that value to get my coefficient of determination. So let me go back to our Google Docs here. Google Sheets, I mean. And let's look at this. I'll just hide this for now. And so my coefficient of determination is going to be my explained variation divided by my total deviation, about 0.83. Again, the other way to do it is, let me do first equals correl of BBAA, right? Um, if I can type that. But I need to square this number. So let me go ahead and square this number. And it's the same number. And so this will be, you can do it either method. If I ask you to only find a coefficient of determination, then you can just get the correlation coefficient and square it, and you don't have to do any of the above. For the homework, I will ask you to do the above, the explained, unexplained total, and find the sums of those. But in general, if I only ask for the coefficient of determination, all you need to do is find a correlation coefficient and square it. So the coefficient of determination between blood pressure and age is 0.83. What does this mean? Uh, in 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 really short terms, all this means is that the line of best fit will correctly predict blood pressure 83% of the time. So it will not, it won't perfectly predict it all the time. It will correctly predict it 83% of the time, is basically what this number means. Determination. I just realized I spelled that wrong. And so, and that's pretty much it for the coefficient of determination. In your homework, I will ask you to what percent of changes in the dependent variable can be explained by the independent variable. Essentially, that's just asking you what's the coefficient of determination and using that as a percentage. Okay, one last thing we need to go over, and this is possibly the more complicated part. Oh, I don't need that. The standard error of the estimate. We've already talked about the standard error a little bit before. It's basically what is the average wrongness of my data, right? How wrong am I on average? In this case, how we are going to figure that out, let me just quickly draw a line. So each of these dots are at some distance away from my line, right? Each of these light blue lines basically indicate how wrong am I. And so in this case, in order to find out how wrong I am, I will take the actual data point and subtract it from my predicted data point, right? And if you look at this equation, it is very similar to our unexplained deviation. In fact, the difference there is not explained by our independent variable. And so to calculate this, we're going to be using the unexplained deviation. So standard error, and you will need to write this formula down, is the sum of yi minus y hat I squared over n minus 2. On average, how wrong am I? Is basically what this standard error is doing. A shorter way to write it, if you memorize the formula for the unexplained deviation, is essentially unexplained deviation over the degree of freedom. Remember, n minus 2 is going to be our degree of freedom for this unit. And so this is another way you can write this formula using words instead of symbols. Now on Google Sheets, we actually don't need to use this formula at all, and I'm not going to make you use this formula. On Google Sheets, let me quickly move this so that you can see the formula. Standard error. So using the formula, we already have our unexplained deviation, 1900. So we can equals the square root of the unexplained deviation over count of AA minus 2, right? So however many data points there are minus 2, that'll give me 15.43. The Google Sheets shortcut for standard error is STEYX. STE is standard error of Y on X. So again, dependent, independent, always, dependent, independent, and that will give you the same answer. We will be using the standard error tomorrow, but for today, I don't believe, in the homework, I'm not asking you to do standard error yet, but just know that if I ask for the standard error, it is STEYX. We'll use this more tomorrow. For today, your homework will be to find these numbers down here. These are the numbers you need to be able to figure out, along with these. Let me just highlight these. So these are the main numbers that are new. So explained variation, unexplained variation, total variation, coefficient of determination, and then just explaining that as a percentage in words. The first two questions for correlation coefficient and line of best fit, I'm not requiring you to write something there, but it will be good practice if you need to practice these things. So being able to use equals correl correctly, being able to use equals slope and equals intercept correctly, those are all skills that will be necessary for the test. This data sheet is what you'll be using: years of salary and years of experience and salary, temperature and ice cream sales, and gold price per ton and silver price per ton. This one has a lot of data. So ideally you'll be able to just autofill it. If not, it's a little bit of clicking and dragging, but I think you'll be okay. And so that's pretty much it in terms of new content. I'm gonna keep the video going and do these two extra data sets. If you want to, you can pause the video, go try these two in-class demos yourself, and then see if it is similar to what I did. Or if you feel confident, you can go ahead and get started on your homework. I will be in the Google Classroom during normal class time if anyone has any questions. So if you're gonna head out and do homework, you can go ahead and do that. Otherwise, everyone else, I'll just do the next two data sets as an example. So here we have heights in inches and pulse. As usual, the first thing I'm going to do is find the average of my y. So I'm going to put this as independent and dependent. So here's my average. I'm going to make it just 2 decimal places. And now I want my predicted y values, or my y hats. So equals forecast. at 16 at that, BB, AA, and I'm just gonna autofill, reduce decimal points. Okay. Explained, unexplained, and I'm not gonna do the total column, just because I'm just gonna add these two up later. And here are my sums. So for the explained, as the formula says, let me go back. Okay. As the formula shows, I need to do the predicted values minus the mean. So the predicted values is in the D column. So D2 minus, and I'm just going to type it out, 85.89 squared. And I'm just going to drag this down, equals the sum of what is up there. And so now I have my explained deviation. My unexplained deviation, I need to do the individual points. So these minus the predicted. So it's equal to B2 minus D2 squared. And autofill, but this last one I want it to be the sum. So equals sum of the above. Cool. And the total will be the sum of these two, right? So these are my totals. Coefficient of determination. I can do the division, so explained minus minus total, or I can just do equals Corel BBAA squared, which is pretty much about the same number. In fact, if I make this the same amount of decimal points, it is the same number. This is a really low coefficient of determination. Essentially, this means that height will correctly predict pulse 2% of the time. It is only correct 2% of the time, which is not great. So essentially, this means that height is probably not a good predictor for pulse, which, if we think about it biologically, makes sense. Finally, I will find a standard error, and I am simply going to use stdeyx, BBAA. So my standard error, if I do use it and I'm only correct 2% of the time, when I'm wrong by about 15 points on average. Or in this case, since I'm measuring pulse, I'm wrong by about 15 beats per minute on average. And that's pretty much all you need to do. That would be enough to fill in the things you need to do here. One more example. This one is months and beef. So this one's another long one. So again, first things first, average of my, so that's my X, that's my independent, and this is my dependent. I'll have this be my predicted Y values, or my Y hats. So this is equal to forecast of A2 and then BBAA, and I'm just gonna let it autofill. I'm just gonna scroll down just to make sure that it autofilled properly. Last one should match up so that all works out. Okay, explained, unexplained. So this is going to be a longer one. That's okay. So my explained, let me just move this over. So my explained, as the formula states, it's going to be my predicted minus my mean. So my predicted y values are D2 and my mean is 4.04. So it's equal to this minus 4.04, and I'm going to square this squared. It didn't autofill, that's okay. I'm just going to click and drag all the way down. There we go. And down here, sums, this will be the sum of, and sometimes this pops up. And so if it pops up, you can just click it and it'll just do that for you. Or just press enter, it'll also just autofill for you, which is nice. The unexplained is the, move this down, or these y values, the actual y values minus the predicted values squared. So equals the actual values minus the predicted values squared. This one autofills for me. I'll just let it do it. I don't want to click and drag. Come down here, this last one, I want it to be the sum of this whole thing up here. So the total variation is these two added together. And so my total variation is 280. Coefficient of determination. Again, I can just do the division if I want. 36, or I can do Corel BB AA squared. Same number, or at least close enough. So let's look at this and see what this means. This basically means that if I just have the number of months, it will correctly predict the beef price 36% of the time. Is 36% or about 36.8, so about 37% of the time if we're rounding correctly. And so is 36% indicative that time is a good factor of beef? Well, 36% is still like 1/3, right? The price of beef probably matters with a lot of other things. Exports, inflation, and there's a lot of other factors involved with the price of beef, right? The price of beef food, the price of workers, like how many hours to take care of things. All those factor into the price of beef. And so if we just have time, we're just going to correctly predict it 37% of the time, which is still decent. It's not a great factor, but it is a good enough factor. It's higher than what we had last time, which was 2%. Finally, we're going to do standard error, STEYX of BBAA. And my standard error, if I do predict beef, I will be wrong by an average of about 72 cents, which is fine. If I'm correctly predicting 37% of the time and I'm only off by 72 cents per kilo, that's not the worst thing in the world, right? If I'm correctly predicting 37% of the time, but I'm off by, say, $20 on average, that's much worse, right? And so coefficient of determination can be used in conjunction with standard error to make bigger interpretations. And so that's pretty much it in terms of what you need to do. You can let me know if you have any questions, and I'll be in the Google Classroom. If you started watching when class started, there should be another 10 minutes that you can come in and ask questions. Otherwise, you can work on your homework. And yeah, the whole homework will probably be due just all on Monday. That way we have time to kind of talk through some of the harder parts. And yeah, let me know if you have any questions.